Chapter 8 OSPF OSPF is a linked state routing protocol developed as a replacement to RIP. Although RIP was acceptable in the early days of networking, hop count as a metric wasn't very reliable, and so this protocol became problematic. OSPF has significant advantages over RIP, offering fast convergence and better scaling to the network's growth. In this chapter, we'll cover OSPF, basic singular implementation, and configurations. First, let's talk about OSPF versions. Nowadays, we use OSPF version 2 for IPv4 and OSPF version 3 for IPv6. OSPF is a classless routing protocol, which means it accepts variable length subnet masks and classless inter-domain routing. It's efficient since it uses triggered updates instead of periodic ones. It has fast convergence through the network. It's scalable and allows for hierarchical grouping, and it's secure, supporting Message Digest 5 authentication, which means the routers only accept encrypted updates from peers. OSPF uses the shortest path first algorithm for best path, and the administrative distance of OSPF is 110 by default, and as such it is preferred of the IS-IS protocol and RIP. All routing protocols use messages to exchange route information and build data structures, processed through a routing algorithm to obtain the best route. The three main components of OSPF include data structures, the adjacency, link stat, and forwarding databases, which are kept in RAM. Routing protocol messages, used to discover neighboring routers. And the algorithm. OSPF uses Dijkstra's shortest path first based on cumulative cost to reach destination and creating an SPF tree to calculate best routes. To make OSPF more efficient and scalable, the protocol supports hierarchical routing using areas. An OSPF area is a group of routers that share the same link state information in the link state database. Open shortest path first can be implemented in two ways. Single area. In this configuration, all routers are in the same area, also known as the backbone. And multi-area. Multi-area supports multiple areas in a hierarchical fashion. All areas must connect to the backbone, and routers that interconnect areas are referred as area border routers. An autonomous system can be divided into smaller areas to support hierarchical routing. Routing still occurs between the areas, known as inter-area routing, but many of the processor-intensive routing operations are kept within an area. Now we're going to talk about OSPF messages. OSPF over Ethernet contains Data Link Ethernet Frame Header. It identifies the destination multicast MAC addresses. IP Packet Header. It identifies the IP protocol field 89 that indicates this is an OSPF packet. OSPF Packet Header. It identifies the OSPF packet type, the router ID, and the area ID. OSPF packet type specific data contains the OSPF packet type information. There are 5 types of OSPF messages. The type 1 is the hello packet. It's used to establish and maintain adjacency with other OSPF routers. The type 2 is a database description packet. It contains an abbreviated list of the sending router's link state database. The third type of message is the link state request packet. Receiving routers can then request more information about an entry in the database description by sending an LSR message. The fourth type is the link state update packet, used to reply to link state requests and to announce new information. The link state update is also used to forward OSPF routing updates such as link changes. The fifth type is the link state acknowledgement packet. When a link state update is received, the router sends a link state acknowledgement to confirm receipt of the LSU. Now we will talk about some of these OSPF messages. The hello packet discovers OSPF neighbors and establishes neighbor adjacencies. It advertises parameters on which two routers must agree to become neighbors and elects the designated router and backup designated router on multi-access networks like Ethernet and frame relay. Point-to-point links do not require DR or BDR. Some of the most important fields contained in the OSPF packets are the type. It identifies the type of the packet. the router ID, the area ID from which the packet originated, the network mask, the hello interval, which is the frequency in seconds at which a router sends the hello packets, the router priority, which is used in a DR/BDR election, the dead interval, which is the time in seconds that the router waits to hear from a neighbor before declaring the neighboring router out of service, the designated router's ID, the backup designated router's ID, and the list of neighbors. As we previously mentioned, OSPF hello packets are transmitted to multicast address every 10 seconds on default multi-access and point-to-point networks and 30 seconds on default non-broadcast multi-access networks. The dead interval is the period that the router waits to receive a hello packet before declaring the neighbor down. If the dead interval expires before the router receives a hello packet, OSPF removes the neighbor from LSBD. Then, the router floods with information about the down neighbor on all OSPF-enabled interfaces. Now we will talk about OSPF operation. When an OSPF router is initially connected to a network, it attempts to create adjacencies with neighbors, exchange routing information, calculate best routes, and reach convergence. A router with OSPF enabled transitions through various states. First, it needs to establish the neighbor adjacencies, passing from the down state, where no hello packets are received, and the router starts sending hello packets through its interfaces. Then, it changes to the init state, when it receives hello packets from the neighbors. Then it passes to the two-way state. On Ethernet links, it elects a designated router and a backup designated router. In the second phase, the OSPF router will synchronize its databases. In the X-start state, it negotiates master and slave relationships and DVD packet sequence number. The master initiates the DVD packet exchange. On the exchange state, routers exchange DVD packets. If additional router information is required, the router transitions to the loading state. Otherwise, it transitions to full state. If the router transitions to load state, link state requests and link state updates are used to gain additional route information. And then, it transitions to the full state, establishing neighbor adjacencies. When an OSPF is enabled on an interface, the router must know if there is another OSPF router on the link, so it floods hello packets through all of its interfaces. When a neighboring OSPF-enabled router receives a hello packet with a router ID that is not within its neighbor list, the receiving router attempts to establish an adjacency with the initiating router. When router 1 receives a hello packets list of neighbors containing its own router ID, it transitions from the init state to the two-way state. The action performed in two-way state depends on the type of interconnection between the adjacent routers. If the two adjacent neighbors are interconnected over a point-to-point link, then they immediately transition from the two-way state to the database synchronization phase. If the routers are interconnected over a common Ethernet network, then a designated router and a backup designated router must be elected. Now you may be wondering, why is a designated router and a backup designated router election necessary? In multi-access networks, there are two challenges for OSPF regarding the flooding of LSA. First is the creation of multiple adjacencies. Ethernet networks could potentially interconnect many OSPF routers over a common link. And then is the extensive flooding of LSAs. Link state routers flood their LSAs anytime the OSPF is initialized or when there is a change in this topology. This extensive flooding can become excessive. The solution to this is managing the number of adjacencies and flooding of LSAs on a multi-access network through designated routers. OSPF elects a designated router to be the collection and distribution point for LSAs sent and received. A backup designated router is also elected in case the designated router fails. All other routers become throtters. A throtter is a router that is neither the designated router nor the backup designated router. After the two-way state, routers transition to database synchronization states. In the X-start state, a master and a slave relationship is created between each router. The router with the higher router ID acts as the master for the exchange state. In the exchange state, the master and slave routers exchange one or more database description packets. Each LSA entry header includes information about the link state type, the address of the advertising router, the link's cost, and the sequence number. The router uses the sequence number to determine the newness of the received link state information. Then, router 1 compares the information received with the information it has in its own link state database. If the database description packet has a more current link state entry, the router transitions to the loading state. After all link state requests have been satisfied for a given router, the adjacent routers are considered synchronized and in full state. As long as the neighboring routers continue receiving hello packets, the network and the transmitted LSAs remain in the topology database.
Configuring Single Area OSPF version 2. OSPF version 2 is enabled using router OSPF process ID global configuration mode command. The process ID value represents a number between 1 and 65,535 and is selected by the network administrator. The process ID value is locally significant, which means that it doesn't have to be the same value on the other OSPF routers to establish adjacencies with those neighbors. Router's ID. Every router requires a router ID to participate in an OSPF domain. The router ID can be defined by an administrator or automatically assigned by the router. The router ID is used by the OSPF enable router to uniquely identify the router. The router ID is used by other routers to uniquely identify each router within the OSPF domain and all packets that originate from them. Participate in the election of the DR. When OSPF links become active, the routing device configured with the highest priority is selected the DR. But how does the router determine the router ID? The router ID is explicitly configured using the OSPF router ID read router configuration mode command. The read value is any 32-bit value expressed as an IPv4 address. If the router ID is not explicitly configured, the router chooses the highest IPv4 address of any configured loopback interfaces. This is the next best alternative to assigning a router. If no loopback interfaces are configured, then the router chooses the highest active IPv4 address of any of its physical interfaces. If the router uses the highest IPv4 address for the router ID, the interface doesn't need to be OSPF enabled. This means that the interface address doesn't need to be included in one of the OSPF network commands for the router to use that IP address as the router ID. The only requirement is that the interface is active and in the up state. Configuring an OSPF router ID. Use the router ID read router configuration mode command to manually assign a 32-bit value expressed as an IPv4 address to a router. Modifying a router ID. Sometimes a router ID needs to be changed. For example, when a network administrator establishes a new router ID scheme for the network. However, after a router selects a router ID, an active OSPF router doesn't allow the router ID to be changed until the router is reloaded or the OSPF process cleared. In the first figure, the router ID should be 1.1.1.1. In figure 2, the router ID 1.1.1.1 is being assigned to router 1. Finally, in figure 3, the OSPF routing process is cleared using the clear IP OSPF process privileged exec mode command. The show IP protocols command verifies that the router ID has changed, using a loopback interface as the router ID. A router ID can also be assigned using a loopback interface. The IPv4 address of the loopback interface should be configured using a 32-bit subnet mask. This effectively creates a host route. A 32-bit host route doesn't get advertised as a route to other OSPF routers. Wildcard Mask. OSPF version 2 uses the argument combination of network address wildcard Wildcard Mask to enable OSPF on interfaces. OSPF is classless by design, therefore the Wildcard Mask is always required. A Wildcard Mask is a string of 32 binary digits used by the router to determine which bits of the address to examine for a match. Unlike softnet mask, in a Wildcard Mask, bit 0 matches the corresponding bit value in the address, and bit 1 ignores the corresponding bit value in the address. The network command. In Figure 1 are the required commands to determine which interfaces on router 1 participate in the OSPF version 2 routing process for an area. Notice that the use of wildcard masks to identify the respective interfaces based on their network addresses, because this is a single area OSPF network. All area IDs are set to 0. Figure 2 provides an example of specifying the interface IPv4 address with a quad 0 wide mask. Passive interface. By default, OSPF messages are forwarded out all OSPF enabled interfaces. However, these messages really only need to be sent out interfaces connecting to other OSPF enabled routers. Sending out unneeded messages on a LAN affects the network in 3 ways: inefficient use of bandwidth, inefficient use of resources, and increased security risks. Use the passive interface router configuration mode command to prevent the transmission of routing messages through a router interface, but still allow the network to be advertised to other routers. The show IP protocols command is then used to verify that the gigabit Ethernet interface was passive. OSPF metric equal cost. Recall that a routing protocol uses a metric to determine the best path of a packet across a network. OSPF uses cost as a metric. A lower cost indicates a better path than a higher cost. The cost of an interface is inversely proportional to the bandwidth of the interface. Adjusting the reference bandwidth. OSPF uses a reference bandwidth of 1000 megabits per second for any links that are equal to or faster than a fast Ethernet connection. While this calculation works for fast Ethernet interfaces, it is problematic for links that are faster than 100 megabits per second, because the OSPF metric only uses integers as its final cost of a link. For this reason, from the OSPF perspective, an interface with an interface bandwidth of 100 megabits per second has the same cost as an interface with a bandwidth of 100 gigabits per second. To assist OSPF in making the correct path determination, the reference bandwidth must be changed to a higher value to accommodate networks with links faster than 100 megabits per second. To adjust the reference bandwidth, use the autocost reference bandwidth megabits per second router configuration command. To return to the default reference bandwidth, use the autocost difference bandwidth 100 command. Default interface bandwidth. As with reference bandwidth, interface bandwidth values don't actually affect the speed or capacity of the link. Instead, they are used by OSPF to compute the routing metric. Therefore, it's important that the bandwidth value reflect the actual speed of the link so that routing table has accurate best path information. Although the bandwidth values of the Ethernet interfaces usually match the link speed, some other interfaces may not. Adjusting the interface bandwidth. To adjust the interface bandwidth with the bandwidth kilobits interface configuration command, use no bandwidth command to restore the default value. Manually setting the OSPF cost. As an alternative to setting the default interface bandwidth, the cost can be manually configured on an interface using the IP OSPF cost value interface configuration command. An advantage of configuring a cost over setting the interface bandwidth is that the router doesn't have to calculate the metric when the code is manually configured. In contrast, when the interface bandwidth is configured, the router must calculate the OSPF cost based on the bandwidth. The IP OSPF cost command is useful in multi-vendor environments where non-Cisco routers may use metric other than bandwidth to calculate the OSPF cost. Verify OSPF neighbors. Use the IP OSPF neighbor command to verify that the router has formed an adjacency with the neighbor routers. Verify OSPF protocol settings. The show IP protocols command is a quick way to verify vital OSPF configuration information. Verify OSPF process information. The show IP OSPF command can also be used to examine the OSPF process ID and the router ID. Verify OSPF interface settings. The quickest way to verify OSPF interface settings is to use the show IP OSPF interface command.
Now we're going to talk about OSPF bit. OSPF bit tree is the OSPF bit tree equivalent for exchanging IPv6 prefixes. OSPF bit tree exchanging routing information to populate the IPv6 routing table with remote prefixes. OSPF bit tree also uses the SPF algorithm as a computation engine to determine the best paths throughout the routing domain. OSPF bit 2 and OSPF bit tree each have separate adjacency tables, OSPF topology tables, and IP routing tables. Similarities between OSPF 2 and OSPF bit tree. Link state. OSPF bit 2 and OSPF bit tree are both classless link state routing protocols. A routing algorithm. OSPF bit 2 and OSPF bit tree use the SPF algorithm to make routing decisions. Metric. The RFC for both OSPF bit 2 and OSPF bit tree define the metric as the cost of sending packets out of the interface. Areas. The concept of multiple areas in OSPF bit tree is the same as in OSPF bit 2. OSPF packet types. OSPF bit tree uses the same 5 basic packet types as OSPF bit 2. Neighbor discovery mechanism. OSPF bit 2 and OSPF bit tree use the Hello mechanism to learn about neighboring routers and form adjacencies. However, in OSPF bit tree, there is no requirement for matching subnets to form neighbor adjacencies. This is because neighbor adjacencies are formed using linked local addresses, not global unicast addresses. DR-BDR election process. The DR-BDR election process remains unchanged in OSPF bit tree. Router ID. Both OSPF bit 2 and OSPF bit tree use a 32-bit number for the router ID, represented in duty decimal notation. Typically, this is an IPv4 address. Differences between OSPF bit 2 and OSPF bit 3. Advertises. OSPF bit 2 advertises IPv4 routes, while OSPF bit 3 advertises routes for IPv6. Source address. OSPF bit 2 messages are sourced for the IPv4 address of the exit interface. In OSPF bit 3, OSPF messages are sourced using the link local address of the exit interface. Advertised networks. OSPF bit 2 advertises network using the network router configuration command, while OSPF bit 3 uses the IPv6 OSPF process ID. IP unicast routing. It's enabled by default in IPv4, while the IPv6 unicast routing global configuration command must be configured. Authentication. OSPF bit 2 uses either plaintext authentication and MD5 authentication. OSPF bit 3 uses IPv6 authentication. Link local addresses. Routers running a dynamic routing protocol, such as OSPF, exchange messages between neighbors on the same subnet or link. Routers only need to send and receive routing protocol messages with their directly connected neighbors. An IPv6 link local address enables a device to communicate with other IPv6 enabled devices on the same link and only on that link or subnet. Packets with a source or destination link local address cannot be routed beyond the link from where the packet originated. OSPF bit 3 messages are sent using source IPv6 address and destination IPv6 address. For this one, OSPF bit 3 packets can be sent to a unicast address using the neighbor IPv6 link local address. They can also be sent using a multicast address. Configuring OSPF bit 3. There are a few steps to configure OSPF bit 3. As you see in the image, we have to enable the IPv6 unicast routing. We can configure a link local address. We must configure a 32-bit ID router. You have to configure some other options for the router. Also, we can configure OSPF3 interface specific, and we have to enable IPv6 routing. To explain a little bit better, we're going to use the next topology. In this case, this topology, the routers do not have IPv4 configuration. But if the network have IPv4 and IPv6 configuration, it is known as dual stack network. This means it allows OSPF2 and OSPF3. As you see in the image, we are starting to configure the OSPF3 using the command IPv6 unicast routing. The other stuff is assigning an IPv6 address to some interfaces with a description and ensure that the interfaces will not shut down. With this, the router automatically generates a link local address. To ensure that we configure correctly, we can use the show IPv6 interface brief. Unless configured manually, Cisco routers create a link local address using FEHE:/10 for fix and the UI64 process. But in some cases, when a router automatically generates a link local address, it makes it difficult to recognize and remember those addresses. For this, we can configure a link local address manually. To do this, we select the interface we want, and when we put the IPv6 address command, we have to put a range between FEHE and FEBF. And in the end, we have to add the link local command. To verify we do this correctly, we use the show IPv6 interface brief command. Configuring the OSPF3 router ID. To configure router ID, we use the IPv6 router OSPF command, and we assign a process ID. Like OSPF2, the process ID value is a number between 1 and 65,535, and is chosen by the network administrator. OSPF3 requires a 32-bit router ID to be assigned before OSPF can be enabled on an interface. In the diagram, we see how an ID is chosen. Like OSPF2, OSPF3 uses an explicitly configured router ID first. If none are configured, then the router uses the highest configured IPv4 address of a loopback interface. If none are configured, then the router uses the highest configured IPv4 address of an active interface. If there are no sources of IPv4 addresses on a router, the router displays a console message to configure the router ID manually. To ensure that we correctly configure the router ID, we can use the show IPv6 protocols. If we want to change the router ID, we can do it entering in the IPv6 router OSPF with the process ID and changing the router ID. After that, we have to go to the exit mode and clear the OSPF process. Enabling OSPF3 on interfaces. To enable OSPF3 on our interface, we use the IPv6 OSPF command. To verify this, we can use the show IPv6 OSPF interface brief command and displays the active OSPF3 interfaces. Verify OSPF3. We use the show IPv6 OSPF neighbor to verify that the router has formed an adjacency with its neighboring routes. Now we are talking about the layers. Neighbor ID. The router ID of the neighboring route. 3. The OSPF priority of the interface. Value used in the DDR and BDR election. State. The OSPF state of the interface. Full state means that the router and its neighbor have the identical OSPF LSDB. The dash indicates that no DDR or BGR is required because of the network type. Dead time. The amount of time remaining that the router waits to receive an OSPF hello packet from the neighbor before declaring the neighbor down. This value is reset when the interface receives a hello packet. Interface ID. The interface ID or link ID. Interface. The interface of which this router has formed adjacency with its neighbor. The show IPv6 protocols command is a quick way to verify vital OSPF3 configuration information, including the OSPF process ID, the router ID, and the interfaces enabled for OSPF3. To retrieve and view a summary of OSPF3 enabled interfaces on a router, we use the show IPv6 OSPF interface brief. This command provides specifics about the OSPF routes and routing table.
Thank you for watching Chapter 8, Single Area Open Shortest Path First Routing Protocol. Remember to check cisco.netacad.net's curriculum for more information.